Long and strong. I used to get that throwing journal, man. I don't know if you can hear me, but I appreciate all the stuff you published in the early 2000s. This is more of a chemistry class. I'm a chemistry teacher. Glenn Thompson, I think, is your name. I feel bad if I don't know that. Thank you so much, man. Hello, American chemistry students. My name is Boris Kamikov, and I am a professor of exchange from Russia. And I will do an experiment with you called formula of a hydrate. This molecule, potassium aluminum sulfate, we often call it alum when we buy it in the store. This molecule comes hydrated, means that when you buy it, it comes with water molecules attached to it, clustered to it on a molecular level. Our experiment today is to determine how many water molecules are present for each potassium aluminum sulfate. Excuse me. Now is correct. Apologies. Let me draw a picture of atomic vision of what we are doing with the experiment. Then I will perform it and do some measurements. Potassium aluminum sulfate, SO42. Let's for right now just imagine it as a cluster of these atoms. That is what we're interested in. Now, each atom or molecule of this will be surrounded, and surround is a good term, by waters, H2Os. Now, we don't know how many waters. So I am just drawing just for example. We will take a sample, we will heat this sample and boil off these waters. So when the waters are boiled off from heat, we will reweigh the sample. The sample will be lighter because we heated away the waters. We will know how many grams of waters were boiled off, and we will know how many grams of this is dry. Come, let us do the experiment and do some math. You'll like and enjoy. I hope you can hear me. I am your professor's cousin from Russia doing experiments. Here we do experiments. This should be good. I think that'll work. All right. We shall do an experiment with alum crystals. Remember that the You cannot see the screen, so I don't point the screen. This is the potassium aluminum sulfate with water molecules, just called alum. These are alum crystals. We only need about 2 grams of this. So we have our little scale that comes in our lab kit. Boris recommends you do not store batteries in there because they wear out. Let me see if I don't know if you can read this. So the cup weighs 2.3 grams, but I don't care. Boris don't care about how much these little cup weigh. So we hit the tare function, T-A-R-E, the tare function, and it says 0.0 grams. We only need about 2 grams. So Boris takes spatula. Ooh, these are very hard to scoop. Okay, that's gonna take. We don't use. We try to pour some in. We pour little in. Okay. Oh, Boris gets 1.9 grams. 2.0 grams. Now, Boris, you need to make sure you don't. The instructions say 2.0 grams, but it is more important you write down exactly what the number is. So, for example, my numbers is kind of wavering between 2.0 and 2.1. I say 2.0 for now, but if you happen to weigh out 1.9 grams, that's very good. You just write down what that number is. Boris take his own advice and write down this number. Now, we know initial. We must take note of how it looks because its physical change that we observe will be telling us about the progress of the reaction. So if we note these are very uniform spheres, they look like they were done in a manufacturing plant. This isn't like a raw mined material out of Soviet Russia. It looks very American produced. We will heat this and observe the changes. We will heat for 5 minutes. No, we will heat for 5 minutes and see what happens after 5 minutes. Battery. Here is our flame. Always make sure you do this in a very safe place. You have this flame will be lit. Let me light this. Oh, perfect. Perfect. Boris, say, how you say? Kidding me you are? Boris, how you say in America? RBR or BRB? And we are back. Let's light this flame. Now, one thing about this lantern is the flame is often invisible. So it's going. I see it's going right there. Okay. This cup has the 2.0 grams of our sample. This cup is for safety. If this thing gets out of hand, I can put cup on this. Boris also recommend you probably have a bigger type of cup made of metal. Could be just like any kind of something else to smother it in case this is too small. Could be a cookie sheet, aluminum foil to go over. That's going. There we go. That's 5. Now that's all we do. We observe what's going on here with the crystals. We start timer for 5 minutes. Now Boris is doing this outside. Ooh, look at the bubbles. Look at the bubbles. They happen so fast. Ooh, that's super hot. Let me check camera. Oh, yes. This is what it looks like very quickly. And what Boris is trying to do is just help it heat evenly. And Boris is very silly with bare hand. We'll come back with clamp that you in the lab kit. Take that off. Boris is going to take it off for a minute just to kind of artificially slow it down. So remember, our goal is to just heat off the water. We are not trying to burn or melt the stuff. So we want to be careful. We don't melt things and it gets too hot. If you want to stir it a little bit, you can use, ooh, I hate how that stuff stuck to the tip there. I don't like that. We're trying to heat it gently. Boys recommend you do safety with your test tube clamps and always maintaining character. So Boris is watching the physical change, and you should comment in your lab the changes here. Beads have disappeared. We hear the sizzling and popping. Oh, oi, Boris. Oh, blunder. Very much blunder. Well, it happened in experiment. Very much blunder. So take note of what Boris did wrong. See how I clamped this thing? Like sometimes when you clamp it, it almost slips out. That is very annoying. That is very annoying. So like Boris is clamping it like this. That is Boris make terrible mistake. So in effect, if I was not recording this live, I would start over with my experiment. But I will continue. We will imagine. Oh, Boris is very frustrated. Boris frustrated. But we go on. When Boris drop it, he know there's one or two little bits on the floor. So some did fall out. So will my number, my mass at the end. So in the lab, there are questions about, just mistakes that are possible to make during the lab. Borders made a mistake, and because of this mistake, I know that my numbers at the end will be artificially low because I dropped and some spill out. These are breaks of the games, as you say in America. This is time to learn. We'll just leave that. We'll just leave untouched for a moment. So Boris, looking at this, Boris thinks he sees a little brown, a little change in color. And that Boris doesn't want to change the color. You just want to boil off the water. You don't want to melt it or have it react with oxygen in the atmosphere. So Boris used glass stirring rod to try to crush it up, and maybe get out trapped water. Now this already sounds and feels like something that is drier, like something that has lost its water content, which is a observation we can put down in our journal. We crush, we crush, we crush. Water's heat for another minute. Thirty more. 30 more seconds. Boris will heat. Now what we will do is we will quickly weigh. We are going to do 2 heatings with this experiment. What that means is that right now is we are going to weigh it just quickly and then put it back on the heat for another minute or two and then weigh it a second time. Water's gonna let this cool off a little bit. Very hot. Will melt a little bit on the table. Made more sense. 1.1 gram is the mass after the first heating. One point 1 gram after the first heating. This look like all water is gone. But to double check, you'll heat for another minute or two and see if the mass go down. If it goes down a little bit, then you try a third time. But if the mass is the same after 2 heatings in a row, everything good. This look very much the same. Ooh, it's more brittle, meaning it's easier to crush. We'll just let that go for another 30 seconds. And let's not forget Boris's little mistake, that this number will be artificially low. We will heat for another minute, do a second heating. We are doing our second heating right now. We will weigh this a second time, and if it still weighs 1.1 grama, then we will do our calculations. Roll this down here to cool for a moment. Let us see how much this weigh after second heating. It weighed the same. Fantastic. It weighed the same 1.1. So it wavered between 1.1 and 1.2. It definitely wouldn't get heavier. So this is very good. Before Boris, because we're done with flame, we'll remove it and extinguish flame. That is set up right there. This canister is still hot, and everything here is still hot. The Boris want to place these things all together before doing calculations and make sure things are turned off. There we go. There we go. We are done with experiment. This may be disposed of. Follow the lab instructions for how to dispose of things. But now we do some calculations with some Russian chemistry. All right. Okay. 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 As we say, in America, all's good. Okie dokie. So, American students, excuse me. We are going to now do the calculations for determining how many water molecules, were actually surrounding the molecule of alum, the potassium aluminum sulfate. I draw 4 here as an example. We heated off the aluminum, we heated off the water. And after the second heating, there was no change in mass. So therefore, 0.9 grams of water must have been heated off of this sample. Boris erase cartoon. And the 1.1 gram remaining, that was the dry or anhydrous potassium aluminum sulfate. So we know how many grams of water we evaporated. Therefore, what remains must have been this right here. Now, to determine their molecular ratio, how many atoms compared to atoms, we do not compare masses. We compare moles. Moles is the unit that we count molecules in. We'll just need to clean up his board a little bit. And then we do the scaffold. So, to calculate how many moles of water we have present, we need the molecular weight of water. So we add up those atoms from the periodic table. Oxygen, hydrogen is 18 gram per mole. You'll note that I put this unit in here as the reciprocal or flipped because in the scaffold we make units cancel. So we pick up our calculators or our abacus. We will now get the moles of water that were released. And this would be 0.05 moles. Boris will be with mental math. So that is how many moles of aluminum. Excuse me. moles of water. This is the grams of potassium aluminum sulfate of dry anhydrous after the heating. And we want to know how many moles of this. So we have to add all of this up off the periodic table. Boris need to get a Mendeleev table himself and calculator. Designed by Dmitry Mendeleev. We call this Mendeleev's table back in mother country. We have 1 potassium, 1 aluminum, 2 sulfurs, and 8 oxygens. Aluminum 27, potassium 39. This is 250. All of these atoms added together is 258 grama per mole. We want grama to cancel. Grama cancel. The sulfur mole. Boris not able to do this in head. 0.004. So these are the moles of potassium aluminum sulfate, dry or anhydrous. Now, what we do with these numbers here, these we can compare to find out the ratios of how many water molecules were surrounding each of these. Now we can do that comparison with simple ratio. This ratio tells us for how many molecules of potassium aluminum sulfate, how many water molecules are surrounding. 0.05 divided by 0.004. This come up with number of 12.5. Very interesting conundrum. What does this mean? This means that every molecule of potassium aluminum sulfate is surrounded by 12.5 molecules of water. Now, to have a 0.5 molecule of water is a silly idea and not realistic. So, based on our experiment, and 12.5 is right that in middle. So Boris say, look, we round this to 13 because we round with the point 0.5, we round up. We say there's 13 water molecules surrounding each of the potassium aluminum sulfates. This is how we write the formula. This is how we draw a picture. H2O, 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 H2O. And Boris draw a cartoony picture, but nevertheless it helps show atomic vision. Well, 13. Now, what Boris cannot now. This is final formula that you discovered using simple techniques of heating and weighing using a balance. You discovered something about the atomic level with using very simple techniques. This cartoon picture right here is not very realistic. It is two-dimensional. You need to imagine the 13 water molecules surrounding what's going on there. And lastly, recall that Bohr's make mistake and drop all the tools. So these numbers are not too good, but Bohr's just finished. We hope this helps. You have a wonderful day.